Okay, so we were talking about canonical transformations. Canonical transformations. Okay. And we said that canonical transformations are those transformations which preserve the Poisson bracket conditions, right? So the fundamental Poisson brackets are preserved. You will have Qi with Pj is equal to delta Ij. Okay, these are the fundamental Poisson bracket. You also have Qi with Qj equal to 0. Qj is equal to 0, and also Pi with Pj is equal to 0, capital P, right? Because we know the fundamental Poisson bracket relations. Now, there's another way of checking this. Okay, this is one way of defining the canonical transformations. All right, canonical transformations are the coordinate transformations which preserve the Poisson bracket. Okay, there's an equivalent way of saying this in terms of generating functions. Okay, we saw that yeah, we discussed this thing, all right, by the principle of stationary action. We used the modified principle, and then we got a condition. From there, we found that if f does not explicitly depend on time, then this combination p dq, okay, if there are a number of things, you will have a summation over the minus pi dqi. This has to be a perfect differential. Okay, you can also talk in terms of the generating functions. Okay, this is true if the generating function does not explicitly depend on time. We also saw that if the generating function does not explicitly depend on time, then the old and the new Hamiltonians are the same, because the Hamiltonians are related. The Hamiltonians are related by this k minus h is equal to k is the new, h is the old, is equal to dou f by dou t, or minus of it. Okay, something like that. It's related by the partial derivative of the generating function. Okay. Now, I think we can use these two methods in order to check whether a given transformation is canonical. Okay, so that's what we'll do in today's class. Okay, we'll look at certain transformations and check if they are canonical. Okay, and in some cases we'll be asked to find the generating function. If you are asked to find the generating function, it's easier to use this method because you already get the differential of the generating function. Okay, all right. So the first problem, find alpha and beta. Okay, find alpha and beta if the transformation q is equal to q raised to alpha cos beta p, okay, and capital P is equal to q raised to alpha sin beta p. Okay, so find alpha and beta if this is canonical. This transformation is is a canonical transformation. Okay, this question has been asked, or similar question, to find certain constants. All right, now what equation do we have? We know they have given that this is a canonical transformation, so we can immediately write that q with p is equal to 1. Okay, we have got this condition immediately, so we can we have got an equation relating these two. Let's check where we reach. Okay, what equation we get. Okay. So if you take this thing, it becomes q raised to alpha cos beta p, okay, comma q raised to alpha sin beta p. We have got alpha and beta, which are constants here. Okay, is equal to 1. So not all transformations are good canonical transformations. Okay, now we can just combine the non-zero terms. You see that there's a non-zero term here, q alpha with sin beta p. Okay, q alpha with q alpha is 0, right? So you can take that Poisson bracket, and you will have what you have outside is this thing. Okay, you'll have to pull this out. Okay, so the first thing is we've got q raised to alpha, okay, with sin beta p. Okay, q raised to alpha plus with sin beta p, and you have this q raised to alpha cos beta p outside. Okay, right. And you have one more term. We have got cos beta p with q raised to alpha. Okay, plus cos beta p. I'm taking only the non-zero combination. Okay, cos beta p q raised to alpha. Okay, and you have got this term outside, right? Q raised to alpha sine beta p. Okay. Now this is a slightly complicated function of alpha. Okay, so we'll just use the fundamental Poisson bracket relation. Okay, so when you use the fundamental Poisson bracket relation, it's actually this. You take the derivative of the first thing with respect to q. Okay, there's only one dimension, so there's no summation. You take the derivative of the first thing with respect to q, multiplied by derivative of the second thing with respect to p. Okay, and then in the opposite order with a minus sign. All right, that's how you do it. So you see that the only non-zero term here is the first derivative with respect to q and the second thing derivative with respect to p. Okay, because this first term is explicitly a function of q and the second one is explicitly a function of p only. All right, so there's only one term in this fundamental definition. You will get dou q alpha. Okay, so shall I write it down? You'll get alpha q raised to alpha minus 1. Okay, the derivative of this with respect to q. And then we need the derivative of this one with respect to p. That would be cos beta p multiplied by beta. Okay, you're taking the derivative of this thing with respect to p, partial derivative. The second term is 0. Second term would include dou q alpha by dou p and dou by dou q of sine beta p. That's 0. Right, so I'm not writing it down. And you have got a q raised to alpha cos beta p here. Okay, plus from here. Okay. From here, you see that again the non-zero term is the second term. Am I right? The first term is 0 because if you take the derivative with respect to p here, or a derivative with respect to q of the first term, that's 0. Right? Similarly, the derivative of the second term with respect to p. So the first term is 0. Here you have only the second term. There's a minus sign. So it would be dou by dou p of cos beta p. Okay, what's dou by dou p of cos beta p? That's equal to minus sine beta p, okay, minus sine beta p multiplied by beta, okay, multiplied by dou q alpha by dou q, that is alpha q raised to alpha minus 1, okay, and you have got q raised to alpha sine beta p. Okay, so with some practice you can skip a few steps. All right. Okay, so what do we get here? This becomes, this has to be equal to 1. Am I right? We are demanding that this is equal to 1. So we just combine term here. We got alpha, beta, and q raised to 2 alpha minus 1. Right? We have got alpha, beta, this q raised to alpha minus and q raised to alpha. That becomes q raised to 2 alpha minus 1. Okay, q raised to 2 alpha minus 1. Okay, and cos square beta p. Okay, and here you have plus. Okay, this minus and minus gives you a plus. You have got alpha, beta, again q raised to 2 alpha minus 1. Okay, sine square beta p, sine square. This is equal to 1. This means that these terms are the same. We can just take cos square beta p plus sine square beta p is 1. So this becomes alpha beta q raised to 2 alpha minus 1 is equal to 1. Okay. Now this is the equation we have. How do we find the alpha and beta from this one equation? Okay. Now sometimes we may need more equations than this but here this is sufficient. Okay. So what we notice is that we have said that alpha and beta are constants. Okay. So we make this dimensional analysis. Right, the power of q on right side is 0. Okay, this you can write it as q raised to 0. Okay, alpha and beta are dimensionless. Okay? So the power of q on right hand side is 0. This means that 2 alpha minus 1 has to be equal to 0. I hope this is clear. Now this means that 2 alpha is equal to 1 or alpha is equal to 1 by 2. Okay, we have got alpha equal to 1 by 2. Substitute it here. You see that 1 by 2 beta is equal to 1. Okay, just put alpha equal to half in this equation and you see you get beta equal to 2. Okay, that's one way of doing it. Alpha equal to half and beta equal to 2. All right. You could also do it by demanding the generator, the D. Yeah, you can also find the same thing. You can do it as a homework. Okay, P dq minus P dq is equal to a perfect differential. Okay. So if you are asked to find the generating function, this is what you will do. This equation will also give you the same result. Okay. These are equivalent ways of talking about the canonical transformation. Okay. All right. Now I hope you can solve such problems easily. We will do more problems. Okay, let's do another one. Yeah, here it is. Okay, so they have given the particular transformation like this. Okay, the second problem. Capital Q is equal to small p inverse. Okay, capital Q is small p inverse, and capital P is equal to Q p square. All right. Now the question is this a canonical transformation? Is this a canonical transformation? Okay. Now it's easier to do it with the Poisson bracket. All right. So I ask you to check it. All right. Check the Poisson bracket. Check with whether Q with P is equal to 1. Okay. But in this question, they have also asked us to find the generating function. Generating function. We find F. So we'll have to be. It's better to use the other formulation. Also, it's also good to practice this. So we know this condition dq. Sorry, P dq minus P dq is equal to df. Okay, this is the condition. So if this thing is a perfect differential, then we know that it's a canonical transformation. Also, we can integrate this equation in order to find f. Okay, so what do we get if you do this? Let's just write it down. P dq minus, let's substitute for capital P and dq here. So capital P is q p square. Okay, q p square. All right, and dq. dq is, what's dq? Minus p raised to minus 2. Am I right? Yeah. dp. This means p dq. We've got a plus there. Okay. This goes q dp. Am I right? Yeah. Okay. Now, is this a perfect differential? The question is whether this is a perfect differential. All right. You see that this is a perfect differential. This can easily be written as d of p q. Okay. Because this is the product rule. This will give you p dq plus q dp. Okay. So you see that this combination is a perfect differential, and so we have got a canonical transformation. So we conclude that the transformation is canonical. Is canonical. Okay. We also need to find f. Now, if you get such a thing, all right, you can always try such a combination. You have got, so sometimes when we try this, it may not be really obvious. Okay. Then the first thing you can do is try this combination. All right. We have got p dq here. Okay. So just try d of p q, d of p comma q. All right. So if you have got some function here instead of p, some function of p, and then you can simply always try d of f q. Okay, this try, and most of the time this comes out correctly. Right. For some complicated functions, it may not be immediately obvious that it is a perfect differential. So you can always try this thing. Right? Whatever is here, you take it and put it inside d of whatever is here multiplied by q, and usually that gives, or sometimes it works. Okay. Right. Now we need to find f. Now we know that f is usually written as a function of old and new, right? Old and new. You either write f of q comma q or q comma p, p comma q or p comma p. Old and new. Okay. So we know here that f is equal to p q, right? Because we have got, this is df. All right. Now we need it as a function. We don't need it as a function of old and old. All right. These are the functions of old coordinates and momenta. We need half of them old and half of them new. Right? Now, an easy way to do this is that we see that P inverse here is capital Q. All right. So this means that P is equal to Q inverse. Am I right? So from this equation you get from this equation you get Q inverse is equal to P. Okay, so this is Q by Q. Okay, we just substitute here. So P is equal to Q inverse. You get this is equal to Q inverse Q. All right. Now this is a function of f of Q comma Q. All right. This is good. Which function is this? This was f1. Am I right? This was f1. Is that correct? No, we can always check whether this is correct. Okay. This is of type f1. All right. Now we can always check whether this is right. We know that P has to be equal to dou f by dou q. Okay. In this case, that becomes Q inverse. Do we have it? Yes. P is equal to Q inverse. That's correct. We also have this relation. Capital P is equal to dou f by dou q. Right? Capital P is equal to dou f by dou q with a minus sign. Am I right? With a minus sign. How do we remember? Because q is in the second place there. Right? So that is minus sign. So this is equal to minus q raised to minus 2q. Okay. That's equal to minus q by q square. Okay. Or we can check whether we get this equation. All right. We have got capital P is equal to qp square. All right. Now we know that P is equal to q inverse. Okay. P is equal to q inverse. There's a minus there. Okay. So q is equal to, sorry, q inverse equal to P. So this becomes P square q. Okay. We have got here. So we have reproduced the transformation by these things. Okay. All right. Now, is there any other generating function that would give you the same transformation? Is there any other generating function that would give you the same transformation? Okay. We can also try using inverting this one. All right. So whichever option is given, sometimes more than one generating function will give you the correct answer. So if the option is given, you will have to look at the options and choose the correct one. Let's also try this. All right. We have got PQ here, and we have got from this equation. All right. From this equation, what do we have? We have got P square is equal to P by Q. Okay. We could also do this, and in this case, F becomes this is P square. So P is P raised to half divided by Q raised to half multiplied by Q raised to half. Sorry, Q. Okay. So this is equal to square root of capital P. Okay. Square root of capital P multiplied by. Now, is this a possible generating function? This also could be a possible generating function. You see that this is of type 2. I think this is type 2. Okay. So depending on what options you are given, whether it's a function of Q and capital P or Q and capital Q, you have to choose. Okay, which of this things you use. Okay, so you can get the same canonical transformation from F1 and F2. Right now, if whether we are correct, you have to check this. All right, check. This is F of capital P. Okay. Capital P, yes. All right, I think you can check that. All right, maybe it's, let's go to the next one. Check whether this reproduces, this gives you this transformations. All right. Okay. So I think we didn't do this one. Okay, so we need to check whether the transformation Q is equal to square root. Did we do this? No, square root of 2Q cos 2P. Okay, and capital P is equal to square root of Q sine 2P. Right? Yeah, I think we didn't do it. We need to find whether this is a canonical transformation. Right? So you just check this. Is this thing capital P, right? This is capital P is equal to 1. If this is 1, this is a canonical transformation. And this is easily done. So you see that this is square root of 2Q cos 2P, comma, square root of Q. Sorry, square root of Q. Square root of Q. Okay, there's no 2. Square root of Q cos 2P, square root of Q sine 2P. Okay. Now, is this equal to 1? So I think we better do it. Okay. So if we take the derivative of you know how to combine these terms. You take only the non-zero terms. I'll be quick here. Okay. So again, you combine this with this. That's only non-zero term in the first thing. So that becomes dou by dou q. That becomes 1 by 2 square root of q. Okay. You take dou by dou q of this and dou by dou p of this. That becomes minus sine 2p. Okay. Minus sine 2p multiplied by 2. Am I right? Yes. Multiplied by 2 because you take dou by dou p of this. Okay. And you have got this. I'm sorry. Okay, so you take the derivative. I think I was right. Okay, you take the derivative of this thing with respect to q. You get 1 by 2 square root of q. Okay, and this thing derivative with respect to p. Okay. Should we just simplify it first? I think we can simplify it first. That's easier. Okay, or it doesn't matter. You can do it anyway. So this you can take it as this is equal to. We'll take only those non-zero combinations. Square root of q comma sine 2p. Okay, square root of q comma sine 2p, and you have got square root of q cos 2p outside plus. Okay, you have got cos 2p with root q. Okay, cos 2p with square root of q. Okay, and multiplied by square root of q sine 2p. Is this equal to 1? Right. So this becomes, take the derivative with respect to q, 1 by 2 root q, and derivative of sine 2p. Okay. Derivative of sine 2p. Derivative of sine 2p is cos 2p multiplied by 2. So I'll write this 2 here. And this 2 gets cancelled. Okay. And you have got square root of q cos 2p. The second term is 0. You take the derivative of this with p and derivative of this with q, that's equal to 0. Right. Plus this becomes cos 2p with square root of q. So here you take only the second term, okay, because you need the derivative of this thing with respect to q is equal to 0. You need only the derivative of the first thing with respect to p. And for that, there's a minus sign, and that becomes sine 2p multiplied by 2. Okay, and derivative of this with respect. So there are two minus signs and they get cancelled. Derivative of this thing with respect to q is 1 by 2 root q. Okay, multiplied by square root of q sine 2p. Okay, now this becomes cos 2p cos 2p. That's cos square 2p. Am I right? Plus sine 2p sine 2p. That is sine square 2p. That's equal to 1. So this transformation is canonical. Okay, it is a canonical transformation. All right. So when they ask, they can ask which among the following is true. Right? They'll give certain combination. This is a canonical transformation. The second option they'll give you another transformation. Say this is the canonical transformation. You need to choose which one is the correct transformation. All right? Or sometimes they ask us to find these constants. if given that given transformation is canonical. All right, so all such problems can be asked. Okay. All right, so here is another one. Show that the transformation Q is equal to log 1 by Q sine P, okay, and capital P is equal to Q cot P is canonical, okay, whether this is a canonical transformation, right? Well, let's do this. Let's do this in the other form. We need to practice both these things. Okay. So we need to check whether P dq minus P dq is equal to a perfect differential. Is this a perfect differential? Okay. Now this we can leave as such. What is dq here? dq is 1 by q sine P. I wrote it correctly. Yeah, 1 by q sine P. Okay. So derivative of log is 1 by, the derivative of log x is 1 by x. Okay. And you also have here some other terms. This is minus 1 by q square. Okay. dq sine P. Okay. You need to take derivative of both this. Okay. So derivative of 1 by q is minus dq by q square. And derivative of sine P is cos P dp. Okay. Cos P dp. All right. So I think we better simplify this first. This is equal to, we've got sine P and sine P there, they cancel. We've got 1 by q and a q square there. So you'll get a q over here. So that becomes minus dq by q. Am I right? Yeah. Yes. Okay. Plus we have got cos P divided by sine P. All right. That is cot P. You can write it as cot P dp. Okay. 1 by q and 1 by q gets cancelled. Right. Okay. So this is dq. Now we find this combination P dq minus P dq. So that is P dq minus capital P d capital Q. Okay. Capital P, this thing. Okay. So you get cot P dp minus dq by q. Okay. All right. And you can use this capital P is equal to q cot P. So it's easier to do it. Or should we do it? Yeah, that's easier. Okay. So capital P is equal to q cot P. Okay, I hope this is clear. The step is clear. Okay. We need to find P dq minus capital P dq. Okay. For capital P, we took q cot P. That's the q cot P here. And dq we found here. All right. It is this. Now you just rearrange these terms. You get, so if you take this dq, if you combine this, you got cot P there. Okay. So if you combine it, Okay, so we take dq. This is equal to, we just, okay, let's write it. This is equal to p dq, okay, minus q cot square p dp. All right, yeah, minus q cot square p, q cot square p dp, okay, plus q cot p dq by q, right? Q cot p, q cot p dq by q. So if you combine these terms, this becomes p plus q cot p, okay, so this is easier. Okay, cancel this. So this becomes p plus cot p dq, okay, p plus cot p dq minus this you can write it as it's q cot square p dp, right? Q cot square p dp, right? Now, is this a perfect differential? The question is whether this is a perfect differential, right? Now, it may not be really obvious, but we can always try this thing, okay? We take d of, okay, this thing multiplied by q. Okay, try this. Okay, this is a good thing to try. This is f dq. Okay, so the question is whether this is df. If this is df, then we have got the correct answer. All right, so let's check whether this is true. So if we take this is equal to d of p plus cot p q. All right, do we get this? Do we get back this? So let's check. The first term becomes p plus cot p dq. All right, we got back the first term. What about the second term? You need to take this plus dp, okay, plus so you dp plus cot p. What's the differential of cot p? What's the differential of cot p? I think the derivative of cot p is minus cosecant square p. Okay, so it becomes minus cosecant square p dp multiplied by q. Okay, now dp minus cosecant square p dp. Okay, 1 minus cosecant square p dp is equal to, this becomes p plus cot p dq, okay, plus dp multiplied by 1 minus cosecant square p, that is cot square p. And you have got it there. Okay. Sorry, yeah, 1 plus cot square p is p plus cot square p. 1 plus cos square p is minus cosecant square p. All right. So I'll give you the value. So it's minus. Yeah. You take dp outside, 1 minus cosecant square p is minus cot square p. Okay. So you get this thing. So minus dp cot square p q minus dp cot square p q. So we have got back this term. Okay. So we saw that this term now can be written as a perfect differential. But I hope how we you understand how we did this. Right? What we did is we started with p dq minus p dq, right? And we reached here. Right? So in order to find whether it's a total derivative, we just tried this. Okay, we tried d of the first term multiplied by q. If the first term is immediately reproduced, we check for the second term and we see that the second term is also reproduced. All right. So we say that this is a perfect differential. All right. P dq minus p dq is a perfect differential because you can write it as d of something. So this is a canonical transform. This is the given transformation is a canonical transform. Okay. All right. Now the relation that I used there was this. We have got this trigonometric relations. We have got it's good to remember this, sin square theta plus cos square theta is equal to 1. We have got 1 plus tan square theta is equal to secant square theta. And we also have 1 plus cot square theta is equal to cosecant square theta, all right? That's why 1 minus cosecant square theta here, all right? Or what do we have? 1 minus cosecant square theta is minus cot square theta, all right? That's what we have used there, right? Okay, sometimes you forget this. This we always remember, sine square theta plus cos square theta equal to 1. We also may need these trigonometric identities. So it's a good thing to make a note of all the trigonometric identities and remember them, all right? Okay, so that is a transformation, right? That is a canonical transformation. Can we also find the generating function? Since we found df, let's also try to find the generating function. Okay, what's the generating function? Okay, so we saw that df is equal to d of p plus cot p multiplied by q. Okay, so we can immediately take f as p plus cot p, or we can write it as p plus cot p multiplied by q. Okay, now this is not in the desired form. We need it half in the old coordinates and half as new coordinates. So how do we do that? That's not really obvious here. So I think you will do it as a homework and I'll complete it in the next class, all right, to find the generating function. Okay, there may be a bit complication when you do that, but try this. So you can use the transformation equations that we already have, okay, and invert them and write this as a function of either q and q or q and p or p and p, okay, any of this or combination of this, right? So let's we'll try this. Okay? So you do this as a homework, all right? What is the correct generating function? All right, so how exactly can we integrate this exactly? Right, so I'll complete that in the next class. Let's do another problem. Do you have any doubt, any questions you can ask now? But this is also an important problem. You get one question from me. The generating function, finding generating function, they don't ask so much, but they also always ask a question about finding whether a given transformation is canonical transformation. All right, so is these things clear? Is there any doubt? Do you need some clarification here? Please answer. All right, so I'll just do a few more problems just to be. So here is another one. P is equal to half p square plus q square. Okay, and capital Q is equal to tan inverse of q by p. The question is whether this is a canonical transformation or not. Is this a canonical transformation? Right. Now again, there are different ways to do it. We did the total derivative thing once. So let's do this Poisson bracket. Let's try Poisson bracket of p with q. I'll be quick here. So this is equal to half p square plus q square. You see that here there is p and q. So you'll have to use both terms of the Poisson bracket. Okay, and tan inverse of q by p. Okay, let's find the Poisson bracket and see if this is equal to 1. Okay, so if you do this, this is equal to, so let's immediately start with the thing. All right, so the derivative of the first with respect to q multiplied with the derivative of the second with respect to p and in the opposite order. So if you take the derivative of this thing with respect to q, you get 2q divided by 2. So that's simply q. Okay. Let's write it down. So let's write all the steps. This is equal to dou by dou q of half p square plus q square. Okay, multiplied by dou by dou p of tan inverse of q by p. Okay, minus dou by dou p of half p square plus q square. Okay, multiplied by dou by dou q of tan inverse of Q by P. Okay. All right. Now you just take the derivative. This becomes 2Q divided by 2. So it's simply Q. What's dou by dou P of this thing? Okay, you know that d by dx of tan inverse of x. This is 1 by 1 plus x square. Okay, so that's the standard formula. So you can remember that. Okay? So Q, this becomes multiplied by 1 divided by 1 plus Q square by P square. Okay, that's not all. You also need to take the derivative of this thing. Okay, we are taking derivative with respect to P. So there's also this Q by P term here. That becomes minus Q by P square. Okay, am I right? Is that correct? So you take the derivative of this thing, QP inverse, that's equal to minus QP raised to minus 2. Okay, so that's minus Q by P square. Okay, that's the first term. Okay, that's only the first term. You also need the second term here, minus, this is simply P again. Okay, here you have got Q and here you have got a P, and this becomes dou by dou Q of this thing. Okay, that's again 1 by 1 plus Q square by P square. Okay, multiplied by, you have got Q on the denominator, so just 1 multiplied by dou Q by dou Q is just 1. Okay, so that's all. We just need to simplify this and see if this is equal to 1. And sometimes they may give you a transformation which is not canonical. Okay, you should be able to check. So this is equal to, you just take the LCM. Okay, LCM there, and you see that this is equal to Q P square divided by P square plus Q square. Okay, and you have got minus Q by P square minus P multiplied by, the time is a minus sign somewhere. Okay, let's check. P square divided by Q square plus P square. Okay, just take the LCM and then simplify. I think oh, there's a 1 by P here. Okay, there is a 1 by P there. Okay, because there's also a P here. So this is 1 by P. Okay, all right. So you have to be careful when you take the derivative. Okay, and this becomes Q multiplied by minus Q by P square plus Q square. Okay, minus P square by Q square plus P square. Okay, so there is something wrong here. So this becomes minus Q square plus P square. So minus Q square plus P square divided by P square plus Q square, and that's equal to minus 1. What did we check actually? We checked P with Q, right? I think we checked P with Q. Okay, so we see that P with Q, I'm sorry, we checked P with Q. So we got it as minus 1. Okay, this means that Q with P is equal to plus 1. Okay, so you can check either of this. So this also is a canonical transformation. Okay, this also is a canonical transformation. All right, so there are such problems. I'll just complete a few more, couple of problems more, and then we can move on to some problems involving some complicated, what do you say, some complicated generating function. We need to find generating functions also. Okay, and then we can stop. Now you can also try this. Okay, try the same problem using P dq minus P dq. All right, and see if it is a perfect differential. All right, and the answer you'll get, yeah, I think you'll get it correctly. This is also easy. You will have to take the derivative again with respect to of tan inverse of P by Q, but you can try that. Okay, you try this at home. Now we have got one more question. P is equal to 2 1 plus Q raised to half cos P. Okay, this seems a bit complicated. Sin P, and we have got Q is equal to log 1 plus Q raised to half cos P. Okay, how do we do this? Okay, let's okay, we already did one problem with Poisson bracket. You could try this with the Poisson bracket. We can also try this thing, whether P dq minus capital P dq. Is this a what do you say, a perfect differential? All right, so we can try this. P dq will keep it like that. We have P and capital Q. So you check dq. dq is 1 by, okay, 1 plus Q raised to half cos P, okay, multiplied by, all right, dq. You need to find dq. Log d of log x is 1 by x. So you got 1 by 1 plus Q raised to half cos Q raised to half cos P multiplied by, you need to take the derivative of whatever is in the argument. Okay, so that becomes half Q raised to minus half cos P, okay, and plus Q raised to half sin P. Okay, we've got a dq here. dq plus Q raised to half sin P dp. It's minus because derivative of cos P is minus P. Okay, so it is dq. Can we simplify it? I think at the moment we cannot simplify. Let's also find P dq. Okay, let's also find P dq. P dq is equal to 2 1 plus, this is P, Q raised to half cos P, okay, and you have got a Q raised to half sin P multiplied by, what's our dq? That is 1 divided by 1 plus Q raised to half cos P, okay, and multiplied by half Q raised to minus half cos P. Okay, I'll just write it here, minus Q raised to half sin P dp. Okay, so you see that now there is some simplification going on here. Okay, so these two terms gets cancelled. So we have enough place to write it now. Okay, so this is equal to 2Q raised to half sin P multiplied by, here we have got, let's just expand it, 1 by 2 Q raised to minus half cos P dq, okay, minus 2Q raised to half sin P, multiply to the second term, there's a minus there, and you get Q raised to half sin P dp. All right, yeah, okay. So sometimes it's easy to make a mistake in these things. Okay, so this becomes, these also get cancelled. You get sin P cos P dq, okay, minus, this is 2Q q raised to half here and q raised to half there. So it becomes 2q sine square p. I hope that's correct. All right. Now we need to check this p dq minus capital P dq. Okay, this is what we found. This is simply capital P dq. So we find p dq minus capital P dq. We have here minus sine p cos p dq. Okay, minus though this becomes plus 2q sine square p dp. Is this a perfect differential? Let's combine the terms. We've got dq here and dq there. So that becomes p minus sine p cos p. We know that sine 2p, okay, is equal to 2 sine p cos p. Okay, so sine p cos p can be written as minus sine 2p divided by 2. Okay, and you have got dq plus this is 2q sine square p. Okay, we don't like the squares, so let's write it as 2q. Okay, we have this relation for cos 2p, or cos 2p is equal to 1 minus 2 sine square p. Okay, there is such a relation. It's a good thing to remember. So you see that 2 sine square p is equal to 1 minus cos 2p divided by, sorry, is equal to 1 minus cos 2p. We got here 2q. So this 2, we can write this as q. 2 sine square p is 1 minus cos 2p dp. Okay. All right. Now again, as we said, is this a perfect differential? We just try. Okay, is this, we can write this as d of. Let's just try this. Okay, it's easy to try. Is this, can this be written as d of p minus sine 2p by 2 multiplied by q. Okay, we can check this. The first term is p minus sine 2p by 2 multiplied by dq. Yes, we got it. Plus, what's the second term? You will have, you need to take the derivative of this, right? Q multiplied by dp minus sine 2p derivative is cos 2p. Okay, cos 2p dp, 2 dp. Okay, so this gets cancelled. So that becomes p minus sine 2p by 2 dq plus q 1 minus cos 2p multiplied by dp. Yes, we got it back. All right. So this thing p dq minus p dq minus capital P d capital Q can be written as a perfect differential. You can write this thing as a differential of, this is indeed the differential of p minus sine 2p by 2 multiplied by q. Okay, that's what we have checked. Now, as I said, this is easy. The easy thing to try is this. You take the first thing, okay, and q multiplied by q. Check whether this is d of p minus sine 2p by 2 multiplied by q. That's what we checked and we got it correct. Okay. All right. So you can also find the generating function if it is possible. Sometimes it gets complicated. Find f. So in the next class, we'll do a couple of more problems to find f. Okay, here mainly today's class we have checked whether transformations, given transformations are canonical. All right, there are different ways to do this. Okay, you can also look at the Jacobian of the transformation, the coordinate transformation matrix, but we don't need that. Okay, so all problems can be solved either by checking the Poisson bracket Okay, check the Poisson bracket. Check if this is true. Qi with Pj is equal to delta Ij. If so, that's the canonical transformation. And you also check this thing. You take the combination P dq minus capital P dq, okay, and see if you can write it as a perfect differential. Can we write it as a differential of something? Okay, these are the two ways in which we can do it. Okay. All right. Now we also found for a few simple cases, we found the generating function. In the next class, we'll do a couple of problems more with that, and then move on to infinitesimal canonical transformation. All right. I think this is the only kind of problem that's being asked from here. Okay. Check the previous question papers. The only kind of problem, they ask certain conceptual questions. Other than that, the problem questions is associated with whether a given transformation is canonical or not. Okay. Are there any questions? Okay. Shall we wind up?
Yes, sir. Thank you.
Okay. Thanks.